have found the electric current in the shields, and we know the conductivity of each element, so we know the power losses in each element. But the ampacity, as I said, is limited by the temperature. So next step is to set up and simulate a heat transfer problem. I'm returning back to QuickField. And I will create a new problem. Cable heat. Well, you know, QuickField can simulate problems independently, but QuickField also simulate multiphysics problem. Multiphysics mean that you calculate current distribution in AC magnetics problem, for example, and import the losses from AC magnetics problem to heat transfer problem automatically. And in heat transfer problem, you calculate the temperature distribution. In order to complete the coupling of two problems, both problems should share the same geometry model file. So when I create the heat transfer problem, I specify that the problem type is steady state heat transfer. The length of the cable line is 1 kilometer, but the geometry model is the same that I used for AC magnetic analysis. Now you see there are two problems, AC magnetics and heat transfer, and they share the same geometry model. Well, of course, in heat transfer problem, you should specify thermal properties of each object. Now let's take a closer look at the geometry model again. So for the cover, for the insulation, the thermal conductivity of the cover is 0.3. Thermal conductivity of insulation is 0.3. Thermal conductivity of conductors of copper conductors 380. For the conductor B, 380. For the conductor C, 380. Shields are made of aluminum, so the conductivity of aluminum is 270. The sand has conductivity 0.8, and the soil outside has the conductivity of 1.2. Now the air is excluded from the calculation. I do not specify any thermal conductivity because the air is moving. It's not a unmoving media. Instead of the simulation temperature distribution in the air, I specify the convection boundary condition on the surface. The convection coefficient is 10 and the temperature is 20. You see, these are Celsius because in new version you can specify not only the length units but the temperature units also. You can specify temperature units to be Celsius, Kelvins or Fahrenheit degrees. And at this boundary far away, I believe that the heat flux is 0. Now the thermal problem is ready. We have specified thermal conductivities for each material, but we have not yet specified the heat sources. As I said, this would be the coupled problems. Heat transfer problem will take the results, the Joule heat, from the AC magnetic problem. So in the heat transfer problem, I open the problem properties, I follow to the links, select the data type, generated heat, and choose the problem. This is the AC magnetic problem, and I add this link to the data sources. Okay, now you can see that thermal problem is linked to the AC magnetic problem, and from the AC magnetic problem it takes the generated heat. Now let's run the analysis of the heat transfer problem. Here you can see the temperature distribution in the sand, in the soil, and in the cable, and on the surface. Now let's take a closer look. You see the central conductor temperature is 22 degrees. And the cable surface temperature is 85 degrees. Well, we can again build the contour like this one and take a look at the temperature distribution from the cable center to the cable surface. Here is the central conductor at the temperatures of 92 degrees. This is the temperature drop in the insulation. This is the shield, aluminum shield, and this is the temperature drop in the cover insulation. We know the temperature drop. We can build the contour. We can build the contour here and calculate. I will adjust the field picture and calculate the heat flux. This is the heat flux per 1 kilometer if we divide it by the cable length, so it will be about 20 watts per meter. And if we divide the heat flux by the temperature drop, we can find the thermal resistance of each layer of the insulation. Now, what else we can do with QuickField in this problem? Why QuickField is easy to use? For example, you decided that there is enough space in the trench and you would like to place the cables not in the triangle but in line. What would be the temperature in this case? Let's again run the simulation. First I should run the AC magnetic simulation to calculate the currents in the shields. And you see again the current distribution is not uniform, especially in the shields. Next step, I can run the heat transfer analysis and calculate the temperature distribution. You see the temperature is a bit high, about 1 degree high. It was 92. And you see that the much heated cable is the central cable. If I draw the contour, for example, like this, and take a look at the temperature distribution along this line, I can find that side cables, central conductors, has lower temperature than the central conductor temperature. So this is the disadvantage of the line, of the arrangement of cables in line. Again, you can see that this is temperature is in Celsius degrees, which is a new feature of QuickField 6.3 SP1. Well, of course, all the results you get in QuickField you can copy to Office or to some other application. There is the edit copy picture. You can copy not only the pictures, but for example, take a look at the table. Coordinates along the contour, temperature along the contour. You can copy this table and paste it, for example, in Excel. And make the plot here. I will remove these columns. This is the temperature distribution plot that I made in Excel. Now this was the task of calculating the cable ampacity. I specified some current in the cable and calculated the temperature in the cables.